just going to be a little sample of all of the math that you might expect to encounter in a computing sort of environment, but I've created this series of videos to really try to focus in on what is it that the students who are studying those sorts of programs need. And we're going to start on kind of a 10,000 foot sort of level to study the idea of positional systems at the time learning how, but as is a figure, group, or symbol that denotes a number. So when we say number, we think like the number 7 means 7 things. The fact that we just so happen to represent 7 with this symbol is sort of arbitrary, right? We could do it in any number of different numerals, but this sort of thing is a numeral, and it gets at the idea of 7 things. So for instance, when we see the numeral that has 2573, we normally interpret that as a number, right? 2573. Well, let's break that down. In fact, I just said what this thing means in words. When we see this thing, the way we interpret it is it's 2,573. And due to quirks of the English language, right, the 73, what we really note what that means is it's 7 tens and 3. So if you'll note here, the 1,000, the 100, the tens, right, all of those have a property that we recognize because we worked with scientific notation before. All of those things are powers of 10, right? So 1,000, when we think about 1,000 writing it like so, that means a 1 followed by 3 zeros. Remember how we could represent that in scientific notation? 10. So here, that digit, here, the 1 get 1. Oops. So 71,000 would be 0. And that we remember from our section on exponents once upon a time, the 10 to the 0 gets us 1. And in fact, that's true for any non-zero number. When we take a non-zero number to the first power, we get 1. So let's look at another example here. Let's write out the decimal numeral 71,094 using a base expansion. Oops. So 71,094. So that first digit, the 7, again, you can almost, we're really thinking about like using scientific notation to unpack this thing, right? If you think about how many decimal places you have to move it over to represent it in scientific notation, you have 7 times 10 to the 4th, because we moved it over 4 digits. And then the next thing here, the 1,000, right, is 1 times 10 to the 3rd. Well, the 0 here just means there are no hundreds, right, on top of whatever thousands, 10,000s, etc. that you have. And then we've got 9 times 10 to the 1, and then 4, which we could write this as times 10 to the 0, or we can just write it as plus 4. Those are both equivalent ways of expressing that. Now, it just so happens that we use this decimal numeral system, but you may be familiar with other numeral systems. Cross-culturally, there are tons and tons of different numeral systems. The Mayans had one, the Babylonians had one, lots and lots of different cultures have had their own numeration system, but the one that you've probably encountered is the Roman numeral system. And the Roman numeral system works very differently than the way that we're used to writing these things. Again, you've probably seen some of the stuff. We're not going to get into all of the weird details with how things are expressed, but the basic idea is that the different symbols represent a different number. So I means 1, V means 5, and so on and so forth. I'm not going to require you to memorize those things, but you will see them everywhere. And if you do crosswords, which I do a lot of, then that's a useful thing to know. Well, so when I see MMXXII, if I want to write that as a decimal numeral, here I've got 2 thousands. Here I've got a 10 and another 10, so 2 tens. And then I've got over here 2 ones. So if we think about writing that now, basically you've thought about what the decimal expansion is going to look like. So that's 2,000, there's no hundreds here, and then 2 tens is 20, and then 2 ones. Now, one of the things that we're going to talk about briefly here is why is it that place value systems are so superior to a numeration system like this? So the one that we use, it's called the Hindu-Arabic numeral system, comes from Indian mathematicians back in the like 2nd, 3rd, 4th century, and then it made its way through Arab traders, and then eventually into Western Europe sometime in the Middle Ages. So imagine though, we're back in ancient Rome, and we're trying to do some addition, right? I'm trying to add this thing and that thing. Well, I guess the first thing we'll have to do is figure out how things group together, right? Let's think about the ones first. I've got I over here, that's 3, and then I, that's 2, so that works out to be 5, right? So that works out to be V. Well, what's next? Okay, so I just accounted for those things. I've got now a V, and this V that I have right here, so V, and another V. Well, that's 2 V's combined, right? 5 plus 5 combines to be 10, so that's 15. So now I've accounted for, what, these symbols and that symbol there. And now I go on, I've got an X and an X, so I've got another X and an X. Well, X plus X is XX. So now if we add in this thing, I've got 3 X's and then a V. Okay, so now I've dealt with my X's, now I have to go up to my next thing, right? Just like I'm making change, basically. So I've got L and L. So if we remember that both of those are 50, L plus L works out to be C. And now we've got that C from all those things here, and I've got C, 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 and then another C, and then another C. C plus C plus C plus C plus C. So that is 500. We have a separate symbol to denote that. That is denoted by D. So that means I've got this thing, I've got this thing. So this works out to be DXXV. And this is without even getting into the weird way that you represent numbers like 9, for instance, if you're familiar with Roman numerals. And it took us kind of a long time. It's not a very good algorithm. And one of the huge ideas in computing is the notion of an algorithm. We're trying to accomplish some problem through some predictable process. And we want to develop a rule or system of rules that tells us how to do that. And it's just kind of inefficient to do this. So I'm not going to require you to do this sort of things. This is really just an illustration to try to get you thinking about what's really going on in the place value system. That's really what this whole exercise, this whole section is going to be about. So as I mentioned, elementary school mathematics, when it comes down to it, a lot of it is learning the place value system and how to do these various algorithms for addition, subtraction, multiplication, and division within it. So we're going to revisit how to do those things when we start changing this. And I'm going to start with a very sort of tactile example, which actually has applications to college basketball of all things. Let's suppose that we counted in a different way. So let's say we counted starting with the fingers on our right hand. This is my right hand. And we're going to start with 0. And then I'm going to count my first finger here, starting with your thumb, why not? And then that would be 1, 2, 3, 4, 5. Right? So we can count the numbers 0 through 5 in that way. Well, I've run out of fingers. So the way that I'm going to count the next one is I'm going to start, just to signify that I've finished counting on this hand, the next number is going to be 6, you know? So I'm going to denote one finger on my left hand to be 6. So when I do that, I reset back down to 0 on my right hand, and then I keep going. So then we're going to have 7 and then 8. So I've got 2 fingers up on my right hand and 1 finger on my left hand. So 2 fingers on the right hand, and then 1 on the left hand. And now another question here to continue this, how far would we need to count to have 2 fingers up on our left hand? So if we continue this process, right, so we were at 1 on our left hand, 2 on our right, that was 8, 9, 10, 11. Well, the next one I'm going to get to 12, so that means I'm going to have 2 fingers up on my right hand. So excuse me, 2 fingers up on my left hand when I get to 12. And I'm going to write these things in words just because we're going to find that numerals are going to become very deceiving in this chapter here. So how far could we go based off of this? Well, we're up to 12, and then we would keep going, right? So 13, 14, 15, 16, 17. The next one would be 18. You might start to note a pattern here, right? I counted up to 1 finger on my left hand with 6, and then 12, and then 18. So then it would be continuing on that pattern, 24, and then 30, right? So that would be, I could represent 30 with all fingers on the left hand. And then I could keep going with my right hand, right? 31, 2, 3, 4, 5. So I could get up to plus another 5 on the right hand. So then I could do 35. So this system would allow me to represent all numbers from 0 to 35. In other words, there'd be 36 possibilities all in all. I'm going to get back to the college basketball application of that. The way that this gets used is in college basketball, you can only have the jersey numbers 0 through 5. And if someone has a foul called on them, the way the referees indicate that is they'll use one hand to indicate the first number of that player's jersey and then the other hand to indicate the second number of that player's jersey. So you can only ever have any of those numbers. Technically, you can also do double zero as well, but we won't get into that part. So what's going on here when I'm representing this? Well, my different hands have a different value associated with them, right? The fingers on my right hand each just count as 1, but the fingers on my left hand each count as 6. So 6, 12, 18, etc. So anytime we have these sort of different values associated with different positions, right? Right hand versus left hand, we get this place value system. So a place value system is a numeral system in which the contribution of some digit to the value of a number is going to be the value of that digit, so however much that numerically indicates, and then multiplied by a factor that is determined by its position. We're getting slightly technical with some of the numbers here, so and some of this printing didn't quite come off. There we go. So when we're talking about a numeral representing some sort of number, we see that different things have some position, right? And that position can be marked by an index. And we're going to use that index in the same way that we did our powers of 10 that we saw before. The rightmost one is going to be 0, and then we're going to count up as we go to the left. Each of these things represents some digit, and the way that we're going to denote that this thing is a number in base 10 is with what we call the radix. So again, just to note this again, the symbols we use to denote different values are called the digits. And then the position of each digit is how far away it is from the rightmost number, right? And we count this using its index from right to left. And then the values of the base used in the expansions is called the radix. And we're always going to have the rightmost index being 0. So let's, now that we've developed this bit of terminology, let's revisit the example that we have shown above here. So we just said, what's the possible number of fingers being held up for each, how many fingers can you hold up for each hand? Well, you can hold up 0, 1, 2, 3, 4, or 5. And I'll go ahead and note those with our standard decimal numerals. But the difference here is that on any given one hand, I can't count beyond that, right? If I'm only limited to what I can represent on my hands, all I can do is between 0 and 5 fingers. So the radix here, here's the tricky bit, I can represent 6 different numerals here. So the radix here would be 6. I'm gonna write that with the word, but we could also write it with a traditional numeral as well. So now let's imagine here, let's use that notation that we just did right there. So here, the way we're going to represent this, same as we did before, except now the first digit is going to tell me the number of fingers on my left hand, and the second digit is going to be the number of fingers on my right hand. Remember, the ones on my right hand just counted the way that they were, and the ones on my left hand counted for 6 times as much. So if we saw the number 1, 5, and this was in base 6, then that first digit is being multiplied by 6. So it's being counted 6 times as much as the actual number of fingers being held up. If I have 1 finger up on my left hand, it's worth 6. If I have 5 fingers up on my right hand, that's worth 5. So all in all, we would have, if we thought about this in base 10, this would be 11. Now, normally we would just write the number 11 and be done with it, but since we are now talking about different things here, representing this 1, 5 is not 15. I'm going to try really hard to make sure I don't slip up with the language throughout these units here. But the 1 and the 5 indicate 1 finger on the left hand, 5 fingers on the right hand, which has a total value of 11 if we're thinking about this in base 10. Next one, so again, 3 fingers up on the left hand. There we go, 3 fingers. And then 1 finger up on the right hand, so each of the fingers on the left hand gets counted 6 times their actual value. So this would represent 3 times 6 plus 1. And again, note here we're thinking order of operations, right? 3 times 6 is not as 18, plus 1 is 19. So that would mean 19 when represented at base 10. Lastly, if we saw this number 5 followed by a 0, that would be 5 fingers up on the left hand, each of those is worth 6. So we're going to take 5 times 6, and then add, well, just 0, right? So if we just had 5 fingers up on the left hand, that would be worth 30 in our base 10 numeral system. So we can go from a number of fingers that we're holding up into a decimal number. But we could also go backwards. We could take this number represented by a decimal numeral and then try to represent it in base 6 notation. So if we wanted to get up to 16, well, let's think. 6, 12, 18. 18 is too far. So I could have 2 fingers up on my left hand, that would get me to 12. And now I need 1, 2, 3, 4 fingers up on my right hand to have 2 times 6, which is 12, plus 4 would be 16. So this would have to be 2 fingers on the left hand, and then 4 on the right. So the first digit represents the number of fingers on the left hand, so 2. The second digit represents the number of fingers on the right hand. And then this thing would be written as a base 6, right? It's not 24. It is not 2 10s and 4 1s. It is, remember what this is, 2 times 6 plus 4, right? So this digit represents the number of factors of 6 that I have. It's really weird because we're so used to numbers being something different. It's going to take a bit, but fortunately, it's going to be the main thing we do in a lot of these sections here. Well, we might be dissatisfied with this, right? Counting up from 0 to 35 isn't maybe all we want to do, right? We might want to count beyond that. So let's say we kept going. Let's say we use the toes on our right foot. Well, I can't really show you that right now without some odd camera angles here, so you'll just have to take my word for it. But let's keep going on this. If we counted up to 35, right? This was 5 fingers on my left hand, each of which are worth 6. That's worth 30. Add another 5 fingers on my right hand. That gets us up to 35. So the next number that's going to make us reset is going to take us to 36. I'm gonna write it in words, right? And then also note, I could indicate this in base 10, but I want to be very, very specific because now we're using numerals to represent different things. I'm gonna make sure to write the radix down right there. Well, we would follow the exact same process with this before, right? We would get to 36, and then we start counting 37, 38, 39, 40, 41, 42, right, with our toe up, and so on and so forth. So I'd be able to count another 35 on my hands before I would have to reset again. So if we were to add 35, right, showing that one right toe plus 35 would get me 36 plus 35, which is 71, and then the next number, so if we kept counting on our toes, the next number would get us to 72. In other words, you might see the patterns going on here. Of course, let me make sure I write the radix down there. Each toe would now be worth 36. So suppose we added in another digit here. So let's say I had 2, 3, 4 in this base 6. Well, each toe is worth 36. So here, the way we can think about this is this number 2 is really 2 times 36, or think about it as 6 squared. We would add to that, again, the number of fingers on my left hand are multiplied by 6, and then the number of fingers on my right hand are just each counted as 1. What we just said here, 2 toes, 2 times 36, right? Think, again, order of operations, square the 6 first, it's 36. Double that, you get 72. These are all base 10 numerals. This thing is 18. Add 4 to that, so that's 90 plus 4 would get me 94 in base 10. All right, so we're going to develop some more like algorithms and standard ways to do that, right? This particular numeration system is not the way that we do it. There are cultures that have used base 6 numeral systems before. So we're going to instead, though, focus on the ones that are going to be relevant for computing. So we'll talk about that a little bit more in the next several sections. So while we're thinking about this, let's think a little bit more about digits. By the way, that last example, talking about the word digits, you might think, where else have you heard that word digits? Well, that's what we use to describe our fingers, right? So that's really, when we're thinking about digits, we're kind of thinking about it as like, what can I count in all of the following systems? So our normal base 10 numeral system, right? 10 is 2 different numerals. It's got the 1 and the counting of 1. We got 2, 3, to figure out how many digits I can represent in all of the following systems. So our normal base 10 numeral system, right? We think we start counting at 1, we got 2, 3, 4, 5, 6, 7, 8, and 9. But no, 10 is not a numeral, right? 10 is 2 different numerals. It's got the 1 and the 0. So the 0 is the other numeral that we can represent. So each number in our positional system can only take on a value between 0 and 9. But very important lesson in computing, when you start counting at 0, you end up with one more when you get to the end, right? So if we stop counting at 9, having started counting at 0, we have 10 things all in all. So that's the system we're familiar with. 2 systems that are common in computing. The first one especially so. The second one, a little less common nowadays, but still in a number of computing systems. So binary, if we have base 2, it means we're only allowed 2 digits. Well, if we think about what digits we're allowed here, we have to give ourselves 0, because we need to account for the possibility that the value, we might not be representing any number of those things, right? We want to give ourselves the possibility of having no 10s in decimal, so we could write a number like 107. And similarly for binary, which means we're going to allow ourselves a 0, we're going to allow ourselves 1, and that's all we get, because we only get 2 digits in binary. Now in octal, which is base 8, you can see that oct prefix, we're going to start with 0, and then we're going to count until we get up to 7 digits, or excuse me, 8 digits. Just like happened with decimal, that means that we are going to, since we started counting at 0, get up to 7, and then that's all we have. So the big idea here is that if we have base b, the only digits that we can represent are the digits 0 through 1 less than the value of b. So now we're going to introduce the general process for what it means to do a base expansion for base b. So the example that we looked at in the preceding couple of pages here with those fingers on hands, we saw that at the very end, let me go back to it for a second, right, that the toes that we were counting were each worth 36, or 6 squared. So however many toes we were having on our right foot, we represented that, we multiplied that number by 6 squared. So this 6 here, we note, not coincidentally, is the radix here. It's the base of my numeral system. So that exact idea is going to be exactly the same for any base system. So for instance, when I have 7, 3 in base 8 in octal, that 7 indicates the number of powers of 8, or number of factors of 8 I have, excuse me. So I've got 7 factors of 8, and then that last digit just counts for exactly what it's worth. 7 times 8, we remember, is 56 here. So actually, if I'm just doing the base expansion, we stop there. You'll see some problems like this on the homework. When they're asking you to do base expansion, they're actually just asking you to stop there. So you've got 7 factors of 8, and that last digit represents 3. When we see a 101 in base 2 in binary, well, you might actually start to think about doing this in sort of the reverse order, right? That rightmost digit is just worth itself, 1. And now the digit to its left represents the base to the power of its index, right? So the index here is 0, the index here is 1. So this is 0 times our base to the 1 power. And then right here, this one is 1 times the base of 2 to the radix, the base, which is 2. We could also represent the number 11201 in what's called ternary, base 3. So let's think about this. Okay, let's think about the index first, right? The index of the rightmost one is 0, and then the one to the left of that has an index of 1. Let me write this down. The one to the left of that has an index of 2, and so on and so forth. Now remember, the index indicates the power that I'm taking the base to. So this first number 1 is being multiplied by my base, which is 3, taken to the power of the index. So that thing is worth 1 times 3 to the 4. The next digit is also a 1. That's being multiplied by 3, right? The base taken to the power of the index, 3, and so on, right? Everything is being multiplied by some power of 3. And those powers are decreasing as we go from left to right. So that 2 that we have here is being multiplied by 3 to the power of the index, 2. Continuing on in this fashion, the next digit 0, well, it doesn't really matter what 0 is multiplied by, but just to continue the pattern, that is being multiplied by 3 to the power of 1. The very last thing is being multiplied by 3 to the power of 0, or we could just represent it as it's just that value it has itself, it's just the value 1. All right. So we'll do a couple more examples like this with one extra little bit here. That's our last page for these notes. So we'll note here, in these examples we're about to do, when we're converting into a base 10 numeral system, I mentioned this before, it's very, very important here, we want to make sure that we write the radix of 10 in the bottom right corner. So that's going to be very, very important so that we can avoid any ambiguity here. So we're going to convert these following numerals into a numeral with base 10. So here I've got of 2. My radix is 5, so the base that I'm multiplying each of these numbers by is going to be 5 to each of these respective powers. So the 4 is being multiplied by 5 squared. My 3 is being multiplied by 5, and then my 1 is just by itself. So now we're going to express this as a numeral in base 10, so we're going to finish out the thing we didn't do on the last page. So this is 4 times 25, and then 3 times 5, I can just do that, right? That's 15, and then plus 1. So here, I've got 4 times 25 is 100, and then 15 plus 1 is 16. So this number here, if I was being very pedantic, I would take note that all of these things are base 10 numerals, right? That's a base 10 numeral, that's a base 10 numeral, that's a base 10 numeral, that's a base 10 numeral. That's a little bit excessive, I think. The main point that we're trying to get at here is that when I get to the end here, this number is 116, right? 100, 110, and 6 ones. So each of these things are being represented in the normal way that we think about numbers, the base 10 numeral system. So we're going to make sure that we write that little 10 down there to avoid any potential ambiguity whatsoever. You'll see a couple of exercises like this on the homework where to avoid ambiguity, they just write the word here instead of the numeral and decimal that we associate with the number 16. So 28 in base 16. I did it. I caught myself. So this number here, 28, is not 28, but when we represent it in base 16, the idea here is that first digit, right? We've got an index of 1 and an index of 0. So that first one tells me the number of powers of 16 that I have. And then the second digit tells me just the number of ones that I have. So this number, which isn't 28, but I slipped up, knew it was going to happen sometime. 2 16s is 32. Plus 8 would get me 40, but again, this is literally 40 when I'm writing this number. So I'm writing this numeral here to represent the number 40 in base 10. I leave that little 10 down there in the bottom right. We're going to do a bunch more with binary. In fact, the next section is completely dedicated to working with binary. So with this binary digit, we're going to get really good at this stuff in a minute. But again, my indices here, starting at the rightmost one, is 0, and then 1, and then 2, and then 3. So that is going to indicate the exponent of my base that I'm multiplying each of these digits by. So the first digit is being multiplied by my base to the third power, and then my second digit is being multiplied by the base to the second power. The third digit is being multiplied by the base to the first power, and the last digit is just doing its own thing. It is equal to the value that we see there. So what does this number mean? How much is the value here? Well, we've got 1 times 2 cubed. 2 cubed is 8, and then that's nothing. 1 times 2 is 2, and then plus 1. So all in all, I've got 11. But we can easily mistake this number as a number in binary, right? As a binary numeral, which is not what we want to indicate, right? We want to say that this is legit 11, right? So we're going to write that here with that little base 10 down there. One last one here, 5021 in base 6. So once more, thinking about the index of the different digits I have here. The first digit 5 is being multiplied by 6 to the power of 3. The second digit is being multiplied by 6 to the power of 2. The third digit is being multiplied by 6 to the power of 1, and so on. The last digit is just worth that value itself. So I'll let you compute this, but 6 cubed, useful thing to know, is 36 times 6 is 216. That's worth nothing, of course. 2 times 6 is 12, and then 1. So let's see, 5 times 216. 5 times 16 is 80. 5 times 200 is 1,000. So that's 1,080. Feel free to use a calculator on this stuff. You don't have to do it in your head. But again, all these are base 10 numerals that we're working with. We've got 1,080 plus 12 plus 1. It's going to be 1,092, 1,093. Again, I do mean 1,093, so write that with base 10. So in the subsequent sections that we're about to do, we're going to focus particularly on 2 bases, but there's 3 bases that are most useful for computing. We'll talk about why that is the case in the next section. But generally speaking, computers are going to represent numbers in one of 3 bases. Binary, which is base 2. Octal, which as we mentioned is base 8. And then the other big one, hexadecimal. Hexadecimal, which is going to be the trickier one, is going to be base 16. The fact that the base is bigger than the decimal numeral system is going to present some problems, some challenges for us, some new things to learn. And it may be the case, by the way, that if you've dealt with computers before, this sort of stuff that we're about to do may actually be quite a bit more familiar. We've taken the 10,000-foot view here in this section, and then in the next couple of sections here, we're going to explore in much more detail working in binary and hexadecimal.